Good afternoon. Welcome to Krishna's class. We continue with our exploration compactness. Now, we have shown that in R, compact sets are characterized as closed and bounded sets. Or with the usual method. However, if X is an infinite set with D, the metric D as discrete metric, then closed and boundedness does not characterize compact sets. For instance, then X is indeed closed. See, XD is bounded as well as closed. But not compact. So only in certain circumstances you have this closed and bounded property together characterizes compact sets. Now we give another example. Let E be the interval minus root 2 to root 2 intersection. That means all rational numbers in the interval minus root 2 to plus root in the open interval. Now this set is closed and bounded. In Q. I am not talking about in R. This is closed and bounded in Q. That is Q with the usual metric. That is x minus y dxy equal to Okay. Now we have the closed bounded interval is closed in a therefore which implies uh, closed interval minus root 2 intersection q is closed in q, which is the same as therefore it is closed in q. Okay, so this is closed in, therefore this is closed in. Now minus root 2 is bounded that's obvious because it is actually mod x less than or equal. Now we want to show that it's not. Why? So we produce a open cover for the set which does not have a finite subcover. For let 2n defined by minus root 2 plus 1 by n for 1, 2, 3, etc. So the union of un provides a covering for set. let open. Now you can easily verify that infinity. See, this is what is happening. Minus root 2 plus root, and what you are taking is this is root 2 minus 1 by n, and this is root 2 plus 1 by, and this is root 2 minus minus root 2 plus 1 by n and root 2 minus. So this collection of sets, see, it's a sort of nested intervals, and then you are taking the intersection with q, okay, and that is this un, and therefore you can easily show that this is true. Now this cover, open cover for has no finite. I don't think I have to prove it because it's very easy to see. You see that if there is such a finite subcover, then but finitely many of these kind of sets would give a covering. But then there is a maximum of n, so there are only finitely many, so there is a maximum of n, say capital N, then you see you have, it covers only up to minus root 2 plus 1 by capital N and minus root 2 minus, sorry, plus root 2 minus 1 by capital N, and beyond that it's not covering. So there is some leftover. Okay. This is again something to do with the distribution of rational numbers on an interval. Okay, now another example. Now we prove that, or we give another example of a case where closed and boundedness does not imply compactness. So consider X to be L2. L2 consists of all those XL R with a sigma finite. Now you know that this is a vector space. and norm x2 defined by square root of sigma in fact call it L2 because of this now. That 2 is linked to this 2 that you are. Okay. Therefore, it's a metric space. With D2, see D of xy defined by norm of, well, you are working in a linear space, all these things will make sense. Now consider the standard basis for L2 given by where EK is defined by N is defined by etc. That means E1 is equal to etc. So En has at the nth place 1, elsewhere all 0. So this is the sequence, and you know that satisfies this condition to be that this condition is satisfied to be a member. Now you can verify that norm of En minus Em is equal to root 2 whenever n is not equal to. That's also quite easy because at the nth place there will be 1, and in this difference at the nth place you will get minus 1. Now compute this and take the square root of that. So that is turn out to be. Now consider the open balls Px half okay. Right, before that we claim that B01, which consists of all those x belonging to L2 such that it's closed and bounded but not compact. Quite easy to see that this is closed. There is the closed unit ball. Now this is also bounded because it has a diameter 2. Okay. Because you see that this consists of all those x less than or equal to 1. Therefore, it is bounded. Yes. Therefore, it is bounded. Now we claim that this is not so. Consider a collection of Px half for x belonging to now this is a open cover for L2. Now we claim that this has finite sub. That is what you have is this B is contained in union that is the open cover. So this has no finite subcover. How do we prove that? Suppose it has a finite subcover. Say then that is then there exists J 1 less than or equal to J less than or equal to K such that and M not equal to N such that EM belongs to B R and EN because these are only finitely many and E1, E2, En etc. form an infinite set. Therefore, and it has to be distributed in all these P, X, J half because it's a cover. Therefore, necessarily there should be some Pxj half in which two elements of this, namely Em and En, where M is not equal to N, belongs to it. Now, we know that the distance between Em and En is root 2E norm of En, which is less than or equal to norm of Em En, and each one of this is less than half. One. So you get an observed result, namely root 2 is less than or equal to is less than 1. not possible. Hence, the Bx as contain thus we have successfully produced a open cover for B01 which has no finite circle. Okay. That is B01 is not although is so that's an example where this closed and boundedness fails to show that fails to imply compactness. So it also depends on the metric space that you are working. Not in every metric space this property closed and bounded implies compactness. Although in R and S. See, the point is that this is an infinite dimensional vector space. Okay, so note that. An infinite dimensional complex space. So we give another example, which is again of the same class. The unit ball in C01 with compact. Again, it's a bounded. And what are these? Okay, C01 is scalar complex value such that are continuous. All continuous functions on the interval 0, 1. Now we define norm infinity is which exists, and this is a norm on this class. This is what is called the soup norm. And now, what is the unit ball? The unit ball is the following. So let B contained in say very poor notation. Yes, sir. Now we claim B is closed and bounded, not common. It's a closed unit ball, but it is not bounded. Oh, sorry, it is not common. To devise a an open cover for this, what we do is let Fn functions be defined by explain what it is. Equal to 0 whenever this is equal to n into n minus 1 into x minus 1 for 1 by n plus 1 less than or equal to t less than or equal to 1 by. And 1 and 0 for +1 . Okay, so let us look at the geometry. Let us explore what these functions are. I mean, eventually it is from this exploration we finally write down the equation of the functions. So what we have is this. This is the interval 0 to 1. And suppose this is 1 by, and this is 1 by n plus 1, and this is n minus 1, and this is 1. Now, up to 0, the function is, the graph of the function is 0. And here you see that the function is a straight line segment. This, and then it's another straight line segment. There, this is that. And this is actually point over right here. And then this is it. Okay. One minus n is negative, n is negative. So what about the x lying between 1 by n and 1 by n minus 1? So negative. Okay, right. Yeah. So this is the graph of the function. Now you see that if you take fm and fn, suppose you choose that you can work out. This is something which you should do. Now you can use this technique. So now show that there exists a an open cover for what is this collection? B contained in Now for that, what you do is you observe that BF Yeah. Now you take this. So you take the collection B X by X belonging to is an open cover. We shall use a similar an argument, similar in the previous. So it's almost just word to word you can construct an argument similar. Okay. Therefore, this is another example where the closed unit ball B is not compact. However, although it is closed and bounded. Okay. So that completes some exploration on that. Now we pass on to okay. So first let us look at R2 consists of with the usual addition and scalar multiplication, it becomes a vector space and it's a non-linear space, and that's the so every element is of the form x1. So let us look at the geometry. Okay, in this, what we do is we first observe that is this is the analog of C. Here S is a S is a square. It's a closed square that you have in R2. Now let us draw the pictures. This is this is 0 R. And this is the square that you have. And you have coordinates for all this. Now, the procedure to show that this is compact is exactly as we did it in the case of closed bounded intervals in R. So assume, what you do is you assume this is not compact. So what do we mean by this is compact? This is compact means that every open cover has a finite subcover. The negation of that is that there exists, suppose this is S. So S not compact implies there exists a open cover S with no finite subcover. Okay, no finite subcover. Then look at this 4 quadrants that you, 4 squares that you have which make up S. Okay. Now you see that this also produces a cover, an open cover for every one of these 4 squares. And if that does not have a finite subcover, then one of these squares, so you call this 1, 2, 3, 4. So one of these squares for which this becomes an open cover has no finite subcover. Okay, so that's what it is. constitute S has an open cover, no finite subcover. How do you argue this? Suppose all the four squares for which the given cover is an open cover has finite subcovers. Then you see that the whole thing would have an open cover with finite subcover. So if to violate that, at least one of these squares should have the property that the given cover is an open cover for it with no finite subcover. So then you can subdivide this again into four equal squares. So one of them should have no finite subcover. So divide is an open cover for and at least one of them and if this is that square, then what you do? Again subdivide and so on. So you keep getting, so continue this process. Then we can get a, so let Sn Vidya. And what you have is that Sn plus 1 Sn. Therefore, what one gets is you have, so there exists a sequence An, the bounded sequence, and Cn and one can estimate the nature of this both bounded and monotone. C and A and perspective. Now you can, as before, show that the corresponding sequence that you have below and converges. Further, one has A equal to B and C equal to. Thus, the intersection of these cells is the singleton point. Now take yes. A UN, yes, belonging to UN since open and you see we have AC having a open cover with a finite subcover, which is a contradiction. Hence, this is the outline of it. Now, a generalization is that it's a direct generalization. And this is actually, in fact, this is actually this is contained in. If you want, you can write this here. Okay. One. So this is in the first R, this is in the second R, and so on. It's a part of. So this is compact. Okay. So that's the general result. Now we make the following observation. We have already proved that any compact Hence, every compact subset of bounded. Is the converse true? That is a closed bounded subset of Rn. This is the question that you ask. So, is the converse true? Now, let B be a Rn. Since B is bounded, there exists R positive such that E is enclosed in one to A. We are using the same notations. Okay. What does this mean? Therefore, B is a closed subset of a compact set. Which we know is compact. Okay. Therefore, hence we have here is the Heinborel theorem. A subset of Ri is compact if and only if is closed and bounded. That's the one that. This is the Heinborel theorem. Rn. So in Rn, we can characterize all compact sets as closed and bounded subsets. With the warning that this is not in general true in a metric space. Okay, I think it's a nice place to stop for the day. So, thank you very much.